How's the sound? Sound test.
How's the sound? Sound test.
Sounds. We got sound. We got visuals. Howdy, howdy. Oh, I can probably adjust that a little bit. Howdy. It is Sunday. It's our Sunday chill stream. I have some stats questions to go over from Math 243. Final exam review, like practice questions. I also have frozen breakfast burritos. Well, they're not frozen now, obviously. They're hot and nice now. Just quick little pockets of energy. That's what I like about breakfast burritos. Hi, I'm Ryan, the calculus tutor. I do these streams a few times a week to answer math questions for free. That's what I'm about. Helping people with math with as few barriers as possible. And I have some questions that I'm going to go over that are related to the final exam for Math 243Z. I've looked up before what the Z signifies, and I just can't keep it in my head. Anyway, from University of Oregon, Math 243Z. Just like always, we start by emphasizing abolish ICE. The stream has actually begun. We'll get rid of that. This will be one of the last sessions with this Miro board. I'm going to switch to a spring 2026 Miro board soon, and so it will not be nearly as laggy for me. And I might partway through. There might be a part 1 and a part 2 of the spring board because, yeah. Anyway, we start off each session saying abolish ICE. Abolish ICE, abolish ICE, abolish ICE. That organization, that federal agency, has proven itself incapable of interacting with the American populace. Masked police snatching people off the streets, shooting people in the streets. We don't need it. So I'm going to keep pushing. Abolish ICE. There'll be elections coming up. We have our midterms coming up. Please vote. You don't have to agree with me. I just want you to vote. The more people who vote, the more we can be certain that what we have is what we as a country have chosen to have. So for now, let's transition into our work for the day. So this Math 243 final review, these practice problems. I'm going to be working on some of the free response questions from this. I'm starting at question 19 because I've already worked through the earlier problems one-on-one with a student. And so I'm just working through the rest of these now. If we're going to use a calculator, we'll show what we do in the calculator. If we use a table, we'll say what table we're using, that sort of stuff. Okay. I need my glasses. No wonder things don't look quite as sharp. What's going on with my Miro board? There we are. Excuse me while I eat on stream. I made these and then forgot about them while I was getting ready for the stream. And so now I have them, and it's on stream, but that's fine. We'll deal with it. All right. First things first, let's put a timestamp on this. Do I usually put a colon? I don't, and actually, I usually don't capitalize it either. Okay, timestamp. We're gonna call this 1535 for this one. All right, so let's look at what we got going on here. The length of human pregnancies varies according to a distribution that is approximately normal, with mean 260 days and standard deviation 16 days. What is the probability that the average pregnancy length for 6 randomly chosen women exceeds 270 days? Right, so exceeds 270 days. All right, so we have a normal distribution with population. So the data that they gave us, right, they gave us mu, which is equal to 260, right? I'm using mu and not x bar because this is population data. And they also give us standard deviation, which is 16, which is also from the population. How do we know? It didn't tell us it's from the population, but it didn't tell it, but what it's saying is the length of human pregnancies varies, right? No caveats, no categories, like nothing to narrow that down. So they're just talking universally population wise. We're just assume this is true across the population. Population of humans. Okay, cool. Our X value, here, let's make this. Our X value is 270, and we actually want it to be greater than or equal to 270. That is our N value. Our sample size is 6. So what we're doing here is we're saying, given this population data and how much, given this information about the variation of pregnancy lengths for the whole population, what's the likelihood that you could take 6 random women, 6 random people who can get pregnant, or who are pregnant, and that their average, the average of just those 6, would be 270 days or greater, right? So just for just one individual, that's not even one standard deviation above the mean. So it's going to be a little bit less than 50%. However, to get a group whose average is greater than 270, that means we need either 6 people who are exactly 270, so 6 people who are exactly 10 above the mean, or we need a few people who are at like 275 and a few people who are at 265, say, both of which, like 3 people at 275, 3 people at 265, that would average out to 270. That's still 3 people all above the mean, right? But remember, it's like a 50-50 shot that any individual is going to be above or below the mean. So that's a lot. So that's kind of unlikely. So we should expect, and this is always a good thing to do, is as you're looking through the problem, figure out what you expect. I expect a value definitely less than 50%, probably less than 40%, right? That's just basic ballpark. But let's work out what we actually need to do here, all right? So here, let's draw it. I think it can always be handy to give yourself a little sketch of the situation, right? Here's our 260. Let's go out 1 standard deviation. So this would be a distance of 16, so that's 276, right? And then we could also go down 1 standard deviation. And that would be 254, but we don't really care about the below. And then what we want is 270 right here, right? So that's 270. And we want it to exceed. So we're interested in all of this space. What percentage? Because remember, everything under the curve, all of this represents 100% of all of the possible pregnancy lengths, right? And they're getting those lengths are getting exceedingly rare as you go either really far below or really far above the average. It clusters near the average. Okay, so what we need to do is our process here is we're going to figure out how many standard deviations, but these are standard deviations adjusted to be standard deviations of samples of size 6, right? And so for that, we want to calculate SE, which is just your your sigma, your standard deviation over n, right? So this is 16 over the square root of it. I'm so sorry. Over the square root of 6. And that's going to equal approximately, I don't have my calculator open. There we go. 16 over the square root of 6 is approximately 6.53. What this is, this SE, actually, let me make sure I'm defining that correctly. Yeah. This is an SE is an estimation of the standard deviation for a sample of size n. Boom. And that's all it is. It's a value we use just like we use the standard deviation, but the standard deviation in this case is the standard deviation of individuals, how much individuals vary within the population. And that's not what we're after. We're after how much do samples of size 6 vary, right? Because that's what we're dealing with. Okay, cool. And so this is what we're treating as our standard deviation. And notice this 270 is now more than one standard deviation above the mean, right? And if we think back to like our empirical rule, the 60, I forget all the numbers. The 68, 95, 99.7 rule, right? So that puts us 18% above the mean, which puts us 34 wide, right? So half of it has to be 34. That puts us at 84% above. That makes this marker right here. That makes all of this space over here at least 84%. So we're actually, which makes this space potentially 16% or less. And so actually it's going to be less because we're more than one standard deviation away. That's just me sort of continuing to make sense of the problem as we go. If what I just said there doesn't make sense to you, don't worry about it, right? But I do want you to figure out on your own, or ask yourself, how do I make sense of, how do I estimate this? What do I know? And I was using the 68, 95, 99.7 rule, right? Which is called the empirical rule. All right. Anyway, back into this. So what we want to know, how many of these standard errors above the mean we currently are. Well, the way we do that is we take, we're calculating a z-value. That's what a z-value is. A z-value is the number of standard deviations above or below the mean. So we want a z-score, right? Actually, we can define that here as well. Z-score is just the number of standard deviations or standard errors above or away from the mean, above or below the mean. And so that's what we're after. Z is equal to our x value minus our population mean, mu, divided by that SE value, right? So we can plug in 270. The order here only matters because if you do it in this order, if your x value is above the mean, you get a positive number. If it's below, you get a negative number. And so the negative sign matches up. This is 260, of course, and we calculated our SE to be about 6.53. I'm going to end up using all of the decimal places here when I calculate it. So if you calculate this on your own and only use 2 decimal places, your answer is going to look slightly different than for mine. But yeah, if we do that, we'll call this and actually, this could be a good opportunity. You know what? Let's practice something. Let me open my TI calculator. Let's practice inputting this into the calculator. This is a good one to practice on. There's my TI. Okay, so what we're going to do, these are the values we want to plug in. But rather than plug the values in and worry that maybe we plugged in the right values or not, what we're going to do is we're going to figure out our calculator values. Right? So in our calculator, we're going to use a capital X. And this is what we're going to type in. So for our X value, we're going to type in 270 store, which is that little arrow, and we'll do capital X, which will be alpha some number. Okay, cool. For mu, we will type in 260 and we'll store it. I'm just going to store it in M because there isn't a mu. Actually, there might be a mu, but you'd have to dig around for it. And for standard error, I'm just what I'm going to type in actually is I'm actually going to have it calculate it. I'm going to do 16 divided by square root 6, and then I'm going to store that in S. In your calculator, you can't do multi-letter variables. You can only do single letter variables. And so that's what this is. This is to remind us what our values in the calculator are going to look like. And then our calculator command or computation, maybe that's better. That is going to be, we're just going to type in X. We have to put parentheses. And so what I'm writing down is I'm writing down exactly what I'm going to type into the calculator. So we need the top in parentheses. So X minus U. Oh, no, I did M. Sorry. for mu. It's a mu, so that's why I did m instead of u. X minus m, close the parentheses, do divided by s. And then you know what? If we wanted to, we could then store that in z all at once, but we're not going to need that z value again. So perfect. That's what I'm going to type into the calculator. Let me adjust my screen share here. Excellent. Okay. So part of the reason I like to do this is so we're figuring everything out before we even pick up our calculator. And now so now we need to input the values. So we will do 270. We'll hit the store button, which is oh, I guess can you oh, you can see my little dot cursor. Okay, my cursor is just a little dot, but there we go. Right here is a store button that gives us a little arrow. And then alpha right here is how we access the letters associated with every button. So we'll hit alpha so that when I hit store again, actually, what I get is the X instead of the arrow. So I hit that and now it says X and we hit enter. And now 270 is stored in the variable X. Any place I use X in the calculator, it will replace it with 270. Okay, and we want to do the same thing for M. So 260 store alpha, and that way when I hit divided by, it does M instead, and I hit enter. That's stored in there. And now for the next one, I need to do actual little calculation. 16 divided by square root, which is above the x squared. So we do second to get access to that. Square root 6. We arrow out. And then now we want to store that in S. So alpha and natural log here gives me an S. Oops. And hit enter. And now look, there's that 6.53 I'd calculated, but now all of those decimal places are stored in S, and you don't have to worry about how many decimal places. You don't have to worry about typing them all in correctly and all of that jazz. It'll just happen automatically. So what I want to do here is I want to first of all capture this to put in the Miro board as just sort of evidence of what was done in the calculator. So on your exam, what you could do is write down what I'm writing down here. Write down your calculator values, write down your calculator computation. That's all you need to write down, because obviously you can't insert a screenshot of your calculator. But if you write this down, that'll be plenty for your professor. In fact, that's more than most other students are going to do, so you'll be golden. Okay, so there's the values. So now what we do, oh, you can't see that I pasted that in, but there we go, I pasted that in. And so now that we have, now that we have the values in there, we can do our actual computation. So I'll come down here and we will do parentheses. We will do X, I forgot. X, there we go, minus M, close parentheses, divided by, and then just S. There we go. Now hit enter, and it did that entire computation for us. So you can see that there. I'm going to capture it and put it in the board here. All right, here is our computation. Boom, easy peasy. So now we can look at this. Actually, here, give myself a little bit more room. Okay, now we can say, ooh, this is great. This is a value we need. So from here we say, okay, excellent. That's our z-score. That is how many, in this case, standard errors above the mean that 270 average for the sample is, right? Okay, so what do we do with that? So now we use table A to look up this z value, which is 1 point. We're going to round it to 1.53. Table A only goes up to 2 decimal places. Okay, so let me what's a good way to do this? I think I'm just going to grab table A. Yeah. Okay, here's table A. And the way you look stuff up in table A, let me make this visible. Our z-score is 1.53, so I'm going to replace that there. 1.53. Boop. There we go. And now, okay. So the column on the left has the ones digit and the tenths digit, the first digit after the decimal of the z-score. So we're looking for 1.5, which is right. Let's do something contrasty. Here we go, pink. So 1.5. So we're in this row. Right, so the top of this highlighted section. And then the 3, notice the row at the top, they all differ by the second decimal place, the hundredths place. So we're looking for a 3 there. And that's what we're after. We're in this column. So if we come down here, there is our value. So what does that tell us? So table A value is 0.9370. What I didn't include here is the graphic at the top of table A that tells you how to use it. Or how to interpret it, rather. So let's grab that. Scoot table A over to make room for this little graphic. Okay. Move this down. So we can move this up. Okay. Table A value. So look, this tells us table entry for Z is the area under the standard normal curve to the left of Z. That's how much is below. So we interpret this. This is What is happening? Oh, there it goes. It was just lagging. This is the probability that X is below 270. How do I know it's a probability that it's below 270? Because that's the way table A works. It always gives you the probability of the value being less than your X value, right? That's why it's shaded to the left. What we want is to the right. So if we have a probability that something's less than a number, how do we find the probability that's above a number? Well, we just do, so to find the probability that X is greater than 270, we just do 1 minus 0.9370, which is equal to 0.063. I did just do that in my head. You could, of course, type it into a calculator. Yeah, 0.63. And there we go. That's our value. That is our probability. So now we can take that and we can actually write out our answer. And I encourage you to do this on the exam to actually, so put your, actually on the practice at least, there was a box to put your number in. So that you could just have that. But I want to restate it. So the probability that a group of 6 pregnant people, how did they phrase it? Oh, actually, that the, let's say like this, that the length of pregnancy exceeds 270 days for a group of 6 is 6.3%. And so notice I reinterpreted that 0.063 as a percentage. You don't have to do that, but showing that you can fluently work with the numbers and interpret them and write them in different forms is just good to show your teachers, right? It makes them know, confident that you know what you're doing. And that's really all they're after. That's what they're trying to evaluate is, do you understand what you're doing? And there we go. Simple as that. So what did we do here? We needed to find the probability that that the average of a sample exceeded a certain value given population data. So how do we do that? Well, we convert the standard deviation from the population to a standard error by dividing it by the square root of our sample size, right? And that gives us, that's going to give us a smaller value, and that value represents the standard deviation, and is an estimation for the standard deviation of samples of whatever size, in our case, size 6. We then use that standard error, we use it in place of our standard deviation, and we just find how far our X value, the value that we're concerned with, how far away it is from the mean by just doing a subtraction, right? And then we divide it by that standard error to find out how many standard errors fit in that size, right? That's all this Z equation is doing, right? It's just finding the distance and then dividing it by the size to figure out how many standard errors fit in that space. That number is a Z-score. And so we talked about how to do this calculation in our calculator for reliability. And we found that it's 1.5. The Z is 1.53. That means 1.53 standard errors above the mean. And then the thing you do with your Z-score is you typically look it up on table A. Table A always gives you the probability that your the probability that the X value will be below whatever you're looking at. So if you're looking for it to be above, you have to do one last calculation, which is just, it's always 1 minus, right? Because it's either above or below. And we do 1 minus, and that gave us our final probability. And so yeah, there's a 6% chance, right? It's only 10 above. That's less than one regular like population individual standard deviation. At first, it might not seem like it would be that low, but like in order to get an average of 6 people that is that high above the overall average, right? It becomes unlikely, right? Because that means you very likely couldn't have found nobody in your group was probably below the average. Or if they were, that means you have to have somebody else in the group who's really far above the average to balance it out. And that becomes increasingly unlikely, right? So that's how this ends up working. Cool. And yeah, please, I mean, I guess I should check and see if there's comments, but I don't think there are. Yeah. But please, email me questions about this sort of stuff. If you have questions, as you're watching this, please email them to me. All right. Another bite of burrito, and we move on. That was 19. So we do 20. So these are a little messy. Like they have like scribbles on them and stuff, because I'm getting them directly out of a. Well, actually, you know what? I don't think I need to. Hold on. Never mind. I have a clean version of this. Haha, easy. So we'll do that. Okie dokie. We also want our timestamp. Okay, timestamp. We are at, I call it 49:45 here. Excellent. Okay. Dylan wants to determine a 99% confidence interval for the true proportion, P, of high school students in the area who attend their home basketball games. Okay. Out of N randomly selected students, he finds that exactly half attend their home basketball games. About how large would n have to be to get a margin of error less than 0.01 for p? Okay, so we're dealing now with probabilities of proportions and things like that, right? So this is really similar to just looking at the number of people or whatever, but the numbers are being sort of crunched into proportions. So it's how many out of the total amount, right? How many out of, so you take a sample, how many out of the total sample, you extrapolate that and say, okay, that must be somewhere near the proportion for the overall population, right? So Dylan found that half of the sample, so we want a 99% confidence interval. And so a confidence interval, let's talk about that, right? A confidence interval um, um, right, is a range, oops, there we go, a range of values for which the mean of samples of size n will have their mean the mean of I'm trying to figure out how I want to say this actually. A range of values for which the mean of samples. Oh, a range of values which, there we go, contains the mean of samples of size n, a range of values which contains the mean of samples of sign n in a proportion equal to the confidence level. Okay, so what does that mean? Especially like for our purposes. It means that we're trying to find a range of values that if we were to take, so it doesn't tell us the actual sample size here. It just says sample size n. But if we were to take multiple samples of that same size and find their average, we would want 90. So if we were to take 100 samples of size n just over and over again, sample, 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 and you can get the same people in multiple samples, right? It doesn't have to be new people in every sample because it's random. So there's a possibility that people will show back up. But if you take 100 samples, we're looking for a range of values where the mean of 99 of those samples will fall within that interval. And then it's okay if one of them has a mean that is either above or below the range of those values, right? And so we're basically saying we can be pretty sure, we say 99% confident. Essentially, there's a 99% chance that if you take any sample, any random sample of size n from this population, there's a 99% chance that that sample will have an average within that range, which means it contains it somewhere. We don't know exactly what it is, but it contains it somewhere. Okay, so that's what we're after. That's what confidence intervals do. And so the margin of error on a confidence interval, and actually the way a confidence interval looks is you just have some, well, in our case, it's going to be a p hat because it's not an average, it's a proportion. And then, so this is our p hat is our sample, I think. Sample proportion, yep. So it's p hat, which in our case is going to be 50%, but we'll get there, plus or minus, because we're creating a range of values, so we need to go above this proportion and below it, plus or minus the margin of error. And that's it. So you take your proportion, in this case 50%, you add your margin of error, and you also subtract it, and that's your range of values for the true proportion. The mean, I'm going to say the mean or proportion come on. Samples. There we go. We're talking about proportion. It's true for the mean order proportion. Okay. How do we find that margin of error specifically for what am I trying to say? Specifically for proportion. Let me grab the formula because I just want to make sure I'm doing this right. Oh, oops, I forgot this. I forgot something here. This is Z star times the ME times the margin of error. Sorry, this is, so it's that plus how many standard deviations you need to go out to capture whatever confidence level you're looking at. And in fact, let's do, here we go. So these star values are just standardized. You can actually find them on table A, but it's, you have to do like this reverse lookup thing. But these are values that they probably want you to sort of know. So for our purposes, because we're at 99% confidence, we want 2.58. That's going to be our Z star value. That just means we need to be 2.58 standard deviations above the mean and below, or the proportion in this case, above the proportion and below the proportion to make sure we're 99% certain, right? Okay. So with all of that said, my goodness, Um, okay. Sorry, I just wanted to make sure I was going to be. Yeah. So this ME for a proportion, this margin, this margin of error, is going to be a square root. And inside the square root, we're going to take our p hat value. I'm going to write this bigger. Our p hat value, which remember is just the proportion from our sample. I'm sorry. We're going to take that proportion. We're going to multiply it by its complement, essentially. So like the proportion, the proportion that doesn't fit. So like if we found 60%, we do the 0.6 times the remaining percent, which is 0.4. I've looked up what this represents before. It wasn't exactly clear to me what this represents. So actually, this calculation here is a little fuzzy to even me. Might be a good thing for another stream is to investigate that. And then we just divide it by n, right? And this right here tells us sort of the size of our standard error, similar to the last problem, right? But it's a standard error for proportions, sort of like a standard deviation. There we go. So here's the deal, though. Since we know what we want, they tell us that our goal is less than 0.01. So we can take this ME and set it equal to 0.01. They tell us that our p hat value finds that exactly half. So the p value they give us is 0.5. And actually, maybe that's worth writing down separately. Sorry, the Miro board is laggy. Let's do that. So let's do ME is equal to 0.01. P hat is equal to 0.5. Remember, we're doing all of this as decimals. You don't want to compute with actual percentage numbers, 50%. It's not going to work out the way you want. So you convert everything to decimals. And then at the end, you can convert it back to percentages if you want to present your final numbers that way. But we'll do 0.5 times 1 minus 0.5, which is also just going to be 0.5, which is actually the largest this value could possibly be. Right? If this was 0.4 and that was 0.6, we're going to get a slightly smaller number than 0.5 times 0.5. So 50-50 split in your p hat is the largest margin of error you could possibly get for a given sample size, which means we'll be finding, even though it tells us the 50-50 right off the bat, this whatever sample size we find here will, no matter what the p hat is, will always give us a margin of error less than 0.01. So if the proportions weren't quite 50-50 like this, we wouldn't have to change the n. It would still give us a margin of error less than that. All right, and we'll just put n down here. That's the value we're trying to find. And now we can just solve, right? This is just algebra at this point. So we will, to undo the square root, we will square. So we have to square that side. So that'll cancel out the square root. So over here, 0.01 is 0.001, or 0.01 times itself squared. And over here we have 0.5 times 0.5. I'm going to simplify this a little bit, over n. And here's a nice little algebra sort of trick. So I want to get this n out of the denominator, so I can multiply both sides by n. But then over here, n is just going to be multiplying this 0.001, so I'll want to divide by it, right? But that means it'll just go in the denominator. So actually, when you have a value equal to a fraction, and you're trying to solve for the denominator of that fraction, you can just swap those. So we will get n, and that's just a trick. It's just a combination of a couple algebra steps. 0.5 times 0.5 is 0.25. Oops. Yeah, this is 0.0001. I don't know, right? Because this is 100th times 100th. It should not be 1,000th, but a 10,000th. Sorry, this is 0.0001. There we go. Sorry about that. I just left out a 0. And then so this will be 0.0001. Easy. And then we can just do that division. Which I get n is equal to, when I do that calculation, 250,000, which makes me think that probably exceeds the size of the actual population that Dylan is studying. So even if he were to sample the whole population, in which case he wouldn't need to do any stats, he could just, if he sampled the whole population, he could just take the actual proportion. He doesn't have to do any margin of error or any confidence level or confidence interval or anything. Yeah, I want to make sure this is correct. Actually, I have the solutions I could look. Oh, I do have the solutions, but it is very messy. Oh, you know what I did? Oh my gosh. I did. I messed this up. Okay. Oh man, sorry about that, y'all. Oh, I forgot the Z star in there. No wonder. This is Z star times. So this is, oh my gosh, this is ME. It's that plus the margin of error. The margin of error is just how much you go up and how much you go below. But ME contains the z star value. I am so okay. And then we get p hat times 1 minus p hat all over n. So what I forgot to do here, 0.01 is equal to, and here, let me get a different color for our z value here. We can just use pink. 2.58 times that square root, which is going to be 0.5 times 1 minus 0.5 all over our unknown n. Okay. See, so what happened there was I got 250,000, and that seemed really big. However, it could be because maybe part of this question is making you realize that that level of certainty probably isn't possible for Dylan for this type of study. But now, okay. So we can go through here. Now we can do divided by 2.58 on this side, divided by 2.58 on this side. So 0.01 divided by 2.58. Now, granted, we could do all of the algebra and solve this symbolically and get the n by itself, and then do the thing in our calculator where we plug in all the variables and then run a single calculation. Either way is fine. I'm doing this one this way. We could do it the way I did that previous problem where we came up with our calculator values, came up with our calculator computation. I'm just trying to demonstrate multiple ways to work through these, right? And you sort of pick what works for you. All right. So this is a smaller value, which is not going to make things better. Hold on a sec. Nope. Wrong page. Oh, there is one thing we can do here. Well, we'll see. Yeah. So if we do that division, we get 0.0039. It keeps going, but I'm going to cut us off at 4 decimal places. Equals, now we have that square root, and up here, this is 0.5. I'll make the square root bigger since we have a lot of stuff in it. This is 0.5 times 0.5 over n. So we will, of course, square both sides. So that square will cancel out the square root. But then that means, we need to square this value. And I squared all of the decimal places on my calculator. And so it's actually turning in, the numbers are getting so small, it's turning into scientific notation, but that's okay. I get 1.5023 times 10 to the negative fifth. So that would be, we'd actually move this over and then put 4 more zeros before it. So it'd be 0.00015023. And now that's going to equal, up top, we can do this multiplication. That's just 0.25. divided by our in value. And now we do that sort of swaparoo that I was telling you about. Boop, 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 boop. A number equal to a fraction. We want to solve for the denominator, so we can just swap them. So we get, oh no, oh no, it's just frozen. Okay, yeah, you guys can see my feed of the stream just froze. I was like, oh no, you can't see what I'm doing. Okay, we're gonna swap those. And so we end up with n is equal to 0.25 divided by 1.5023 times 10 to the negative fifth, which is crazy. And then so we get n is equal to approximately okay, it is a smaller number. Oh, because we're dividing? Fascinating. Oh, that is bigger than it otherwise was. Okay, yeah. So we get n equals, well, actually, I'm not even getting any decimals here. I'm getting n is equal to 16,641. Now, if we go back, we want the margin of error to be less than 0.01, not equal to it. We want it to be less than that. So this is our sort of answer, but really what we'd want to say is for the margin of error to be less than 0.01, the sample size would need to be at least 16,642. Why 42? Because 41 gives us exactly 0.01. We want it to be less than that, so we need to make the sample size go up. The bigger your sample size, the smaller your margin of error, right? Because you're closer to sampling. The bigger you get, the closer you are to sampling the whole population, right? And so the closer you are to sampling the whole population, the smaller your error needs to be, because you've accounted for more and more variability out in the population. And there we go. That's our value, our answer, I mean. Oh, it's so laggy. It's so laggy. There we go. And actually, here, I'll even make a note. This in value gives us a margin of error equal to 0.01. So if we want less than 0.01, we increase n by 1. And that gives us our value there. So there's an explanation of where that came from. Neat. Take another little bite of burrito. I think we earned it. All right. I got a slightly different answer than the answer in the solution that the professor did, because I used 2.58 and the professor used 2.576 for the Z star value. And I think that's where the discrepancy came from, because it's a discrepancy of less than 80 people, which is a small percentage of this overall number. Okay, cool. Easy peasy. Ba, ba, ba. Let's look at 21, shall we? Oops, too big. And actually, they're wrong size there anyway. There's that. Oh, right. We want to leave some room for our timestamp value. Timestamp is going to be 1. We'll call it 1:22 on the dot. Is what we'll call this one. Okay. So we survey a random sample of 100 students on campus and find that 62 of them have a sibling. Give a 96% confidence interval for the percentage of UO students who have a sibling. Okay, so we're just actually constructing this confidence interval, right? So last time we said a confidence interval for a proportion, right, is equal to your p hat, your sample proportion, plus or minus your margin of error, but we'll just spell it out. That's Z star. There we go. Z star times the square root of p hat times 1 minus p hat all over the size of your sample. Okay. So, I honestly think let's do this on the calculator, right? We can. So our p hat. Oh, so let's do calculator values. Let me label this. I'm doing it this way. I encourage you to do something similar yourself. Spell out the calculator values and then spell out the calculator computation. Actually write them down. It makes it a lot easier to then plug it into your calculator. All right. So our p hat, right? That will just be, so what we're going to do, that's just the percentage, right? So 62 over 100. So we could type it in as 0.62, but like just in case it was weird numbers, I want to show that we can also do 62 divided by 100, and then we will store that in just p. Our Z star if we look back at our previous, it doesn't have a 96% confidence interval. So, yeah, let's talk about, okay, so let's do a little aside. Finding Z star from table A. Okay. So what we need to do here. So we want a 96% confidence interval. So what we're looking for, here's our mean. We want to find a value, z star, right? These distances are z star. So maybe I should put them right there. Z star. This is our p hat. We want this from here to here to be 96%. That dot doesn't mean anything. Right? Which means there's left over is 4%. So this over here has to be 2%. And this right here has to be 2%, which means this value right here is the 98% mark. Right? So this is what makes it hard to figure out these z values manually. But we can find them out manually. So we actually need to find the z value on our table that gives us a value close to 98%. So we're going to be looking up on the inside of the table. And so let me grab that. Make this kind of small, but then we'll zoom in. Okay, so 98%, which is 0.98, right? That's the number we're looking for on the inside here, right? So this is our target. So notice that the numbers at the top, 50%, and they get bigger as you sort of go in the reading direction, left to right and then top to bottom. So here, this is 99.98%. That's way too big. So we're looking for 0.98, 0.99, 0.99, 0.99. Okay, here's a 0.98, but it's 0.9834, 30, 21. So we'll go back up to here to the next line up, 0.9817, 12, 08, 03, 9798. So actually, it's probably right in between here somewhere. And so if we look, this is 2 points. It's somewhere between 2.05 and 2.06. So 2.05 and 2.06. So the middle there is 2.055. So that is the value we're going to use. I wonder if that's the value the teacher used. Teacher just used 2.05. That's fine. Either way, if you want to estimate the middle, because it would be somewhere, it's pretty close to right in the middle. I think 2.055 is a little bit closer to the z star value that we actually want here. There's also a way to get your calculator to spit out this number, but I think that would be a whole aside. Okay. So this is our z star value. That's z star. So we come over here and we say, okay, z star. I know that's behind me. You can see it there. Right, 2.055. Okay, I'm going to put it up here in just a second, though. So we're just going to do 2.055, and we're going to store that just in z. Excellent. Okay, we have p hat. That's all we need, p hat. And then we also need to input our n value. So n is going to be 100, and we're going to store that in n, right? Okay, so once we have that, once we have all those input, what are we going to do? So we need to do our calculator computation. Or computations. So we're going to do, what we're going to type in is we're going to type in P. We'll do minus first so we get the lower end. Minus Z. We can hit times if we want. Times. We'll do a square root. In the way my calculator works, I don't think I'll have internal parentheses inside my square root. No, there's no parentheses inside the square root. So we'll just do the square root. But what we'll need some parentheses anyway for the numerator. We want to keep it all together. So we can do, actually, since it's multiplication, we don't actually need to. So we can do P parenthesis 1 minus P divided by N. Right? There we go. Actually, if we really wanted to, so we don't have to type this all in again, though I do want to show you a way to modify it. Okay, that will give us our lower value. And then we also want to do P plus that same thing, Z times the square root. I don't think you actually need that times there. I think it understands that it's going to be times. There we go. So just one's minus and one's plus. And I want to show you how to input those so you don't have to retype it all back in. Okay, so here I'm going to hit clear and clear off my screen. There we go. Okay, so we need to input our values first, right? So we're going to do 62 divided by 100. And we're going to store that in P, which is right there. Boom. Okay, 0.62. That's what we expect. Then we're going to do 2.055. We're going to store that in Z. Excellent. Then we're going to do 100, and we're going to store that in N. Easy. Okay, so let me grab that so I can throw it in the Miro board. How would it be if I made this all a little bit smaller, moved it over here so I could paste in this right there. Excellent. Okay, there's that. So we can see here, let me get that out of the way. Okay, now we want to do the same thing here. I'll sort of cover that up so it's not confusing. And now we want to start typing in our calculations here. So we will do, so we'll do P, I lost my P, there we go, P minus Z, and we can do times, that's fine. Square root, so that's a second and the x squared, that gives us our square root. And notice it puts us inside the square root, so everything we type from here, so we don't actually need to put, the square root itself doesn't need a set of parentheses. You can put them if you want, but we don't need them. So we'll do P, and then parentheses, 1 minus P. There we go, close parentheses, divided by, and notice how it's extending the square root and keeping all of this inside the square root. What is happening? Oh, there we go. It just wasn't showing the alpha for some reason. Okay. And there we go. And we can hit over to get out of the square root. Not that we need to do anything over there, but now we can hit enter and we get that value. So 0.52. Excellent. That's our lower value of our confidence interval, as far down as 52%. And now, instead of typing this all back in with a plus sign, what we can do is we can cursor up, right? So I'm hitting my up arrow, cursor up until we select that. And then if you hit enter, it brings it back down to the edit area. So the bottom line of this feed is the things you can edit. You can't edit anything up here, but you can go up and select them and individually clear them and things like that. And now we can cursor over. There we go. And the minus is highlighted, so anything we type will replace it. So we just hit plus. And now you don't even have to cursor back over to the end. Now we can just hit enter again, and boom, we have both of our values. So let me capture that. Boom. Okay, we'll go back to this. And we have our values. So our confidence interval is from 0. I'm just going to do 2 decimal places, 52, all the way up to 0.72. And what we figured out with that is that 96, if we took 100 samples, or it doesn't matter how many samples we took, but we took a whole bunch of samples of size 100, 96% of them, their mean would be somewhere in here, which means the true, or their proportion, not their mean, their proportion, the proportion of people that have siblings, if we go back and look at what they were studying, the true proportion for the entire population of students on campus is somewhere between 52% have siblings and 72% have siblings. And we have like 96% confidence that the true mean lies within there. Or sorry, the true proportion. I keep saying that. Excellent. I guess we deserve another bite of let me check that against what the teacher has. That's exactly what the solution says. Okay, there are 2 more. I'm going to do my best to get to both of them. Timestamp here, 139, 40 is our timestamp there. Let me go grab the other piece. Well, actually, let's read through it first, and then I'll go and grab there's multiple parts to this, A, B, C, D. Okay, so a company that manufactures digital thermometers wants to determine whether a new model tends to read higher than the true temperature. So we want to see if it gives an accurate reading. A random sample of 16 thermometers is tested. For each thermometer, the difference in Celsius between the thermometer reading and the true temperature is recorded. Negative values indicate the thermometer reads lower than the true value. That makes sense. The sample has a mean error of 0.5 and a standard deviation of 1.2. Use a 0.01 significance level to test the claim that the population mean error of all thermostats is positive, that they're above. So right off the bat, this is because we're testing just above, this is a one-sided hypothesis test. Okay. So the first part of this is just like it is in any hypothesis testing. Oops, wrong tab there. First thing they want us to do is just establish our null and our alternative hypotheses. The null hypothesis. So when you're doing research like this or studies or whatever, we always start with a null hypothesis. We always go in assuming there is no difference. This is an attempt to systematize non-bias, right? Like we don't want to go in assuming there's a difference because we'll look for it. We want to go in assuming, even though something's different, in this case, a new model of thermometer, we're just going to assume it's going to be exactly the same, and then we'll wait and see what the numbers say about if it is actually truly different. So H0, that's our null hypothesis. And so our null hypothesis, and we're always making our hypotheses, it's a hypothesis about the population, right? We don't need to make a hypothesis about the sample. We have the data from the sample, right? So our null hypothesis is that mu, the average of the population of these new thermometers, right, is that mu, and so in this case, we're talking about the average difference in temperature, right? So that's what mu actually equals. So we want that we are assuming that difference will be 0. These thermometers will work the same as the others. There won't actually be an average difference. However, we do suspect, or we are concerned that they might be too high. So our alternative hypothesis, if our null hypothesis is proven or is shown to not likely be true, and that's what we're ultimately testing, is what's the likelihood that our null hypothesis is true. If our null hypothesis is evaluated to not likely be true, our alternative hypothesis is that we expect that difference in temperature to be positive, to be greater than 0, because we suspect that the new thermometers might give a higher reading. Okay. So we're just investigating the null hypothesis, and we have our alternative hypothesis as as something we can turn to should our null hypothesis not be likely. And that's all we're testing, is what is the likelihood that null hypothesis, that given this information, given this sample, and the details of this sample, what is the likelihood that the null hypothesis is true? That's usually what we're after. So a test statistic is going to be a Z or a T value. In our case, this is going to be a T value. Why? So we use we use T value because only sample data is known. Specifically, the sample standard deviation, or we don't know the population standard deviation. All we have is the sample. Yeah, the sample standard deviation. So we're gonna need a t-value, which is table C. When we use t-values, we need to determine our degrees of freedom. And that's just equal to n minus 1. So it's just going to be, oh, yeah. And we can define our variables someplace, right? We can say, okay, our n is equal to 16. That's up there. So this will be 16 minus 1 is 15. All right. So that's our degrees of freedom. Then the other thing we need is our significance level. Let me go grab. There we go. Ba, ba, ba. Wait, why is this? Okay. So there's a lot going on with table C. Okay. So here's table C. First of all, we know we are in the 15 column, or sorry, row, right? So here we're in the 15 row. Notice there's so degrees of freedom down the side. That tells you what row you need to be in. Then from there, there's a few ways to figure out which column you're in. There's these confidence levels up here. So if we were creating a confidence interval, we could use those. There's also these one-sided and two-sided P. We said initially that we're doing a one-sided test. That because our alternative hypothesis is that that the difference is a greater than, rather than it's just simply not the same, right? That would be two-sided. If we just didn't have a suspicion, we just wondered if it's different at all, that would be two-sided, because we don't suspect if it's above or below, right? So ours is one-sided. So what we do is we go down here to the one-sided and we look for our confidence level, 0.01, or significance level, rather. Sorry. They more or less mean the same thing. So we're in this column. So we go up, we go up, we go up, over, over, over. And so that right there is our T value here. Which is different than what the professor got. Oh, the professor calculated it instead of looking it up. Oh, sorry. I'm so sorry. I used this too early. I'm so silly. We'll come back to this. Hold on. We'll come back to this. That's my bad. Hold on. And that degrees of freedom doesn't matter for this either. So here's what we're going to do. I'm going to go here and we're going to grab all of this stuff. And bring it down. Okay. So sorry about that, y'all. we actually have a formula for our t-value that we can just directly calculate. The t-value is equal to x bar, which is the average of our sample, minus our hypothesized mean, which is 0, over our standard deviation, so S instead of sigma, because it's a sample standard deviation, again, divided by the square root of the sample size, because that standard deviation is the deviation for individuals in the sample, not the standard deviation for the average of samples, right? So we can plug all this in. We know our average was 0.5, they said, right? So we get 0.5, and actually here we can say x bar is 0.5, S is 1.2, that's supposed to be an S. We have in our mu, and actually we could even throw a mu 0 on these, right? Those are our hypothesized mu's. So, okay, so we can come back in here and say 0.5 minus 0 over 1.2 divided by the square root of 16. That's 0.5 divided by 1.2, which is itself divided by 4. This is 0.5 divided by 0.3, which is 5/3, which is 1.67. If we do 2 decimal places. So t equals 1.67. I would put in here t equals, because it is a t-test, right? You have t down here, but your answer is that your test statistic is a t-value 1.67. Okay, excellent. Sorry, you can look up t-values the way I was doing them, but that's for a different thing. Okay, so we have that. So let me move this stuff back. Oh, let me get part C. All right, so part C is finding the p-value based on this test statistic. The p-value, let me just explain this. P-value is the probability that H0, the null hypothesis, is true given this sample data. It's called p-value because it's a probability value, right? And that's ultimately what we're testing when we're doing hypothesis testing. What is the probability that the null hypothesis is true given the sample data we found? So for this, we use table C. And what we're going to do here, so we know we're in this again, the degrees of freedom does come in here. So we know, let me zoom in, our degrees of freedom are 15. So we do know that we are in this row. And what we're looking for, so what are we using table C for? We're using table C to find the t values that how do I want to say this? That contain um, our t-value. Well, actually, we want, since this is a one-sided test, I like to say it, that contain our t-value, right? And so our t-value was 1.67. So if we go down to our table C, we know we're in column 15, or sorry, row 15, I apologize. And we're looking for the numbers that contain, so this right here, 1.67 is between these two numbers. Those are the two values that, so we get 1.341 is less than our t-value, which was 1.67. Yeah, I'll just do it black. 1.67, which is less than the other t-value, 1.753. Right? So that's where we got those from. Ignore the stray mark on there. That's a mark that was in the PDF. I can't get rid of it. Excellent, which means, and now what we do is we go to table C and we look at the p-values down here, right, that correspond with these. So 0.1 and 0.05. So we go up here and we say, and actually here, let me do those with a different color. So then we go down here and we look at these values and we say our p-value is somewhere in between 0.10 and 0.05. 0.10 and 0.05. Excellent. And so what we could say is this is what we could put in here. We don't actually know the true p-value. That's the thing with this table, is it can only give you a range of p-values most of the time, unless you happen to have a t-value that lands perfectly on one of these, in which case I guess it could give you an exact p-value. But yeah, so what we'll say here is we'll say 0.10 is less than p, and or I guess we have to turn those around, don't we? Sorry. Greater than. That doesn't make sense. There we go. Yeah, that is greater than our p-value. Come on, Miro board. Stop lagging on me. There we go. P is somewhere between 0.05 and 0.10, right? So the smallest it could possibly be is 0.05, which means the least probability, but actually it isn't even as low as that, right? So there's at least a probability of 10%. There's at least a probability of 5%, but not a probability quite as high as 10%. And so that's the probability that our null hypothesis is true, which seems kind of low, right? Somewhere between 5 and 10%. But so this is where we go. So now we'll look at part D because it gives us what you do next here. Let me paste it in there. Okay, part D, now that we have this is basically asking, is P less than 0.01? So the significance level tells you how low the probability needs to be in order to reject the null hypothesis, because that's what we're after. If the null hypothesis is extremely unlikely, then we can say, well, it's probably not actually true. The chances that we would get a sample that would give us an incredibly unlikely result, right? Because our sample is likely to give us the most likely result because that's what makes it likely. A single sample is unlikely to give us a very unlikely result. It could, right? It still always could. That's why you want to do multiple samples most of the time, or repeat experiments and things like that, is to make sure that it wasn't a fluke, because you can always get that 1 in a million thing, or that 1 in 100 thing in our case. So is this test significant at the level? So we know from from part C, we know P is greater than 0.05. So which means P is also greater than 0.01. Not less than. Significance means it's less than that, because it's the probability the null hypothesis is true. And if we want to reject the null hypothesis, it has to be unlikely. It has to be unlikely to the level of our to our significance level, right? And the significance level is just the probability. And so our answer is no. It's not significant at that level. It is significant at the 0.0, well, at the 0.10 level. It's not significant at the 0.05 level because we're not less than 0.05. We're still greater than it. 0.01, 0.05, these are pretty common significance levels, but sometimes you want to be really, really sure. So you want a significance level, which is sometimes called an alpha value, of 0.00001 or something like that, right? It really depends on what standard in the field you're studying and things like that. But there we go. That's the end of that question. There is still one more question. I unfortunately have, not unfortunately, I don't want to say it that way. I can't extend the stream here because I have another student. I have a student I'm meeting one-on-one just after this. I do, just to throw it out there, I do offer one-on-one tutoring. Check out my website. You can send me a message there if you're interested in one-on-one tutoring. I have my advertised rate on there, $50 an hour, but that's negotiable. I charge families what fits their budget, or individuals what fits their budget. So if you can afford my $50 an hour, then that's very helpful to me. That helps me pay my bills. But if you can't, I'm totally willing to accept what you're able to pay, because it still helps me pay my bills a little bit, and my priority is helping you with your math. Okay. So yeah, we didn't get quite to question 23. I might maybe pop on after my student. Actually, you know what? What if I do extend a little bit and I push my student back? Yeah. Okay. let's do it. Let's finish this last question off because it's not going to be hard. It's going to be pretty quick. Excellent. That was my student telling me that no problem pushing back 15 minutes. Okay. Here's question 23. Let's get a timestamp on it. (206:15). We'll call it. This problem only has one part. There's not multiple parts to this, so excellent. So there's that. Can make it a little bigger, I think. All right. A biologist surveyed an SRS, a simple random sample, which is what we want, of 21 lizards in a certain region, and found that 12 of them had spots. Using the +4 method to find a 95% confidence interval for the proportion of lizards in this region that have spots. The grammar there is a little off. Okay, so +4 method. Is a technique for correcting small sample bias. Essentially, so it's either small sample bias or if if there's just if the proportion is really really high, like really close to 100% or really close to 0%, right? There's just not enough. This gives us more accurate results when the sample's really small or when the proportion is either really close to 100 or really close to 0. When those things are true, using the regular calculations actually doesn't give us as good a results as using this +4 method. There's some specific conditions, right? So use when oh my gosh, if I could write, NP is greater than or equal to 10. So the number times your proportion. And I guess this should be P hat really. And N times the complementary proportion when both of those are greater than 10. So for ours, N is equal to 21. P hat is equal to 12 over 21. Use when I had these backwards. Okay, 12 over 21, which is approximately 0.5714, just to get a few decimal places in there. Okay, so if we did this, so NP is equal to equals 21. So NP is equal to 12, and 1 minus P is equal to 9. Here we go. So check, right? So because one of these is true, then +4 method is an okay method to use. It will give you better results. So what we do is we take our what I'm going to call P prime, our modified P, right? It's equal to number of successes plus 2. Oh my gosh, that's so. Here I'm just gonna grab this and put it in here because it'll look nicer. There we go. So our P prime is equal to the number of successes plus 2 divided by, and our in prime is plus 4, right? So P prime is that, in prime is n plus 4. So n prime is going to equal 25. P prime is going to equal, number of successes was 12, so 12 plus 2 over 21 plus 4. So this is going to be 14 over 25, which is approximately 0.56. So load our probability a little bit, and there we go, 0.56. Oops, wrong button. So our confidence interval then, now that we've adjusted this, our confidence interval is going to be very similar. It's going to be our P prime, our adjusted P, plus or minus that Z star value. So we'll figure out a Z star for a 95% confidence, times, and this will look familiar, P prime times 1 minus P prime all over N prime. Yeah. All right. And so I say we just do it on our calculator, right? Calculator. Oops. Values. Right. So we need P prime is going to be, and then it actually does work out to exactly 0.56. So we'll do 0.56 and we'll store that just in P. N prime will be 25 and we'll store that just in N. And our Z star value, well, let's figure out our Z star value. We will just go and grab that table that I put. All right, so let's get rid of that. 95, so we're using 1.96. So this will be 1.96 stored in Z. All right, those are our calculator values. Lower those down a little bit. So now that we have those values, let's write what our calculator computations. Do you hear my cat? Destroyer! It's okay. I'll come and give you some soup in a minute. All right. So what we're going to type in, we just want to type in this confidence interval, right? So we're going to type in P, we're going to do minus first, just get the lower end first. P minus Z, and we can do times, that's fine. Times square root, and inside the square root, we'll do P times 1 minus P times, or divided by, rather, N. And then we're also going to do that same thing, but with a plus. Right, and we talked about how you don't have to retype it back in, you can just go and grab it. So, well, I mean, hit full screen. So first, let's get the values in there. So let's clear. I'm just gonna, if you double tap your clear button, it'll clear your whole screen. All those variables are still stored in there. It's just cleared the screen. We want to replace them though. But okay, so we're gonna do 0.56. So we're gonna store that in P. Oops. In P. There we go. We got that. We're going to do 25, store that in N. There we go. We're going to do 1.96 and store that in Z. Excellent. I want to grab that, throw it in the mirror board. Okay. So we now have our calculator values in there. So now that we have our values in there, let's move this over. And now we can type in our computations. So we're going to do P minus Z times square root. So second, that gives us our square root. We're inside the square root now, so we can do P parentheses 1 minus P, oops, P, there we go. Close the parentheses, divided by our in value. And there we go. We hit enter. Gives us our lower level. And then we cursor up using our arrow keys, select our computation there and hit enter, and it brings it back down. And so now we can arrow key over, cursor over, go to our minus sign, hit plus instead, and then hit enter again. And there are both of those computations in there for us. Oops, where's my... Oh, hold on. That one doesn't have the the bottom value. I must have captured my screenshot before the here we go. Before my stream feed was updated. There we go. Okay, so what we're looking for here is So this is a confidence interval. This is a 95% confidence interval. So how we're interpreting this, right? We get two values. This number and this number right there, right? So our 95% confidence interval for the proportion of spotted lizards. Yeah, spotted lizards is, so at a minimum, it's 36.5% to 75.5%. Or you could report it as the decimals. It doesn't really matter. Right there. And what that means is that if we were to take repeated samples of size 21, right, because that was our original sample size, repeated samples of size 21, figure out how many lizards had spots and figure out that percentage, the percentage that have spots in each sample. 95% of the samples we take, the proportion will be somewhere between 36-ish and 75-ish percent. We know the true proportion lies somewhere in there. Is likely to lie somewhere in there. You're super unlikely to take a sample of 21 lizards and find that fewer than 36% have spots, and more than 75% have spots, right? It's a pretty big range, but it's because our sample was so small. With a bigger sample, we can narrow in that confidence interval. And that's that. That is the, so we can go up here. I guess I can put the answer in here. We can say 0.365, comma 0.755. Was it 365? 365, yeah. 755. Perfect. So down there I reported as percentages. Here I reported as decimals. They're both perfectly fine. And there you have it. That is, that's all of that. Please send me follow-up questions, clarifying questions, anything like that. I hope this was helpful. And yeah, I don't know. We're going into finals week for the university, at least. I don't know if I will be doing a Tuesday or Wednesday stream this coming week. I'll just have to see what it looks like, see what sort of questions I have. And then after that is spring break, and like my family's visiting over spring break, and so I'm almost certainly not streaming that week. I might stream next Sunday, but maybe not since it's beginning of spring break. So yeah, keep an eye on my YouTube posts. Keep an eye on the website for when the next stream will be. But with that, I hope this was helpful. I don't know. Get rid of that infinite. But I will be back, especially as we get into spring term and as we come back from spring break. I will definitely be back answering questions. If I get questions submitted to me, I will definitely do a stream, right? But if I don't have questions, I don't always have, something prepared to talk about. I'm trying to get find more and more things to just talk about on stream, but sometimes I don't have it. So all that said, I hope this is helpful. Y'all have a good rest of your weekend. I'll talk to you soon. Bye.